Okay, so today you could download the notes right here, and when you do that, this is what it looks like. But I'm hoping you'll do that later. You can just watch the video for now. And also, after today's kind of notes, you should be able to answer or a lot of the questions on the study guide, and also on the two worksheets that I want you to really concentrate on this weekend, worksheet 1 and worksheet 2, that look like this and like this, so that we can whiteboard them next time that we get together. Okay, so now I'm going to go ahead and get into the presentation. Um, and this is a PowerPoint presentation that I very quickly put together. I don't normally do PowerPoints, you guys know that, but since we have to do it this way, this is this is what we're going to use. Okay, so let's say we're looking at this bridge and this trash truck and this car are sitting on the bridge. And we could analyze this pretty easy. We can look at the masses of the car and the bridge, and we know the distances, let's say, to the truck and to the car, and we know the whole length of the bridge is 60 meters. We could even look at the forces that act on the bridge. There's one from the car, one from the trash truck, one from the bridge right at the center of gravity. There's one on either end, a support force. Um, but here's the question I have. How big are those support forces? We know the sum of those two support forces has to be equal to the sum of the downward forces because it's an equilibrium. But does FB have to be the same size as FA? Probably your gut tells you that since the car and the truck are closer to FB, probably FB is bigger. That's my guess. That's what I'm thinking that you're thinking right now. But we don't know that. If we would use the information that we did last year and write a net force equation, FA plus FB equals the sum of those, or another way to write that, F net, which is 0, equals FA plus FB minus the three downward forces. We still have two unknowns. F net again is 0. That's not unknown. That's 0 because it's not translating. FA and FB are unknown. I don't know either one of them. We know the sum is equal to the sum of those, but we don't know what FA or FB is individually. So we're kind of at a loss. So my point is, the stuff we learned first semester is good up until a point. We really need to use some other information. Specifically, we need to use this idea of torque. So not only is it not translating, it's not rotating. So I can use the idea that the net torque is 0. Now, usually where students get stuck at is, okay, if I want to do net torque, where's the fulcrum? Where's the pivot point? Because you need to know that. Well, the pivot point, truthfully, can be anywhere. It could be rotating about that end, could be rotating about that end, could be rotating anywhere since it's not rotating. We want to pick a pivot point that will make the problem easier. How do we do that? Well, remember that the torque is equal to the force times the distance times the sine of the angle. The distance is between the force and the pivot point. So if we can choose the pivot point just right, maybe we can eliminate one of these two forces. In other words, if we put the pivot point down here at the end, the distance between the force and the pivot point is 0, and there's no torque from FB, and we've eliminated that unknown. Likewise, we could put the pivot point down this end. That eliminates the torque from FA. It's kind of like me pushing on the door at the hinges. It won't rotate. So that's what I want to do. I need to choose a pivot point at one of the two ends. It doesn't really matter. I could put it here in the middle if I wanted to, but I'm still going to have two unknowns. Luckily, I have two equations now, so I could do that. It just would be tougher. I'm going to put the pivot point down at the end, though, in my case. And so then I have the net torque equation equals the torque from B, which is, if you look at this, again, imagine the pivot's right here. B is forcing it up and over, so kind of like this. That would be counterclockwise, so that's going to be a positive torque. F, or the force from the bridge, the truck, and the car, they all go in the opposite direction, kind of like this. Well, that would be clockwise, so those are all negative torques. Now I'm going to plug in what the torque is. It's force times distance times the sine of the angle. Well, the angle for each one of these is 90 degrees. Sine 90 is 1, so it drops out. So it's going to be FB times this distance, 60, minus 900,000 times its distance, which is half of 60, 30, times 320,000 times its distance, which is 40, times the force of the car, which is 9,400, or minus the force of the car times its distance, which is 50. So I'm subtracting all of those. Remember that net torque is 0. It's not rotating. So that means I can just do plug and chug, solve for FB, and I get 671,167 newtons. Now I can plug this back into my first equation. Remember, again, it's not translating either. So Fnet is 0, and now I can solve for FA, and I get FA is 558,233. So in fact, FA is smaller than FB. Kind of follows along with what your gut was, your initial instincts. But here we've proven it. We're going to try another example. Let's say we have somebody that's climbing up this ladder, and we want to figure out how much friction is necessary down here to keep it from falling. So the mass of the ladder is 15 kilograms, mass of the person is 72 kilograms. The ladder is 3 meters, and the person is 1 meter from the end, and the angle down here is 75 degrees. We can go ahead and put in all the forces. Again, forgive me because I didn't use feeler-dealer notation. I put this together really quickly this morning. We have two normal forces, so I'm calling one N1 and the other one N2. One is from the floor, a support force. There's another support force from the wall. I'm calling that N2. So if I wrote my equations here, I would say that Fs, the static friction, must be equal to N2. It's not translating left or right. Further, I would say that N1 must be equal to WL plus WP. It's not translating up or down. And that's what we're going to see here in a second, written a little bit differently. I'm writing Fnet equals Fs minus N2. In other words, this minus this gives me the net force in the x direction, which is 0. Fnet in the y direction would be N1 minus those two forces. Again, Fnet's 0. Plug in those zeros, I get Fs equals N2, something we already said, Fs equals N2. And I get N1 equals the sum of those two, which would be 72 plus 15, that's 87 kilograms times 10, 870 newtons. That's all I could have done last semester. I have two unknowns, Fs and N2, but I want to know what static friction is. If I would have gave you this problem last semester, you couldn't have solved it. But now we can use net torque equaling 0 to solve this problem. So the first thing kids get stuck on is they're like, where do I put my pivot point? Again, you could put your pivot point anywhere because it's not really pivoting. Every place is fine. You would be able to solve the problem. Some places are better than others because they make it easier. Remember, to make it easy, you want to eliminate one of these unknowns. So that means you want to put your pivot point either at this end to get rid of N2, or you want to put it at this end to get rid of Fs. It doesn't really matter. Again, if I put it down here, why does that eliminate N2? It's because its distance from the pivot point is 0. And so the torque would be 0, like pushing, trying to open a door by pushing on the hinges. There's no torque created. I'm going to choose, though, down at this end. That's where I'm going to put my pivot point. Why? Because now I eliminate two torques, N1 and Fs. Those two torques, I should say the torques created by those forces. Now I only have three torques. If I would have put it here, I would have had 1, 2, 3, 4 torques to deal with. I still would have got the right answer. It's just it would have been a little bit more calculations. Okay, so the net torque is going to be equal to the torque from N2. Kind of look at this, right? Down here is a pivot point, so N2 is making it go around this way. That would be counterclockwise, so it's positive. Minus the torque from the person. Notice that force is making it go around this way. That would be clockwise, so that's negative. And minus the torque from the ladder itself, and again, that's going to be clockwise, so it's negative. Remember, torque is force times distance times the sine of the angle. So it's going to be N2 times the distance, which is 3 meters, times the sine of 75 degrees. That's the angle of this. It's the same as this angle. Minus the weight of the person, 720 newtons, times the distance. Set as 1 meter from the end, so it must be 2 meters, times the sine of 15 degrees. That's the angle between the force and the ladder. You could also use this angle here, 165 degrees, because sine of 165 is the same as sine of 15. And then minus the torque from the ladder, which would be 150 newtons, that force, times that distance, which is 1.5 meters, times the sine of 15, or again, you could say sine of 165. Remember, the net torque is 0. It's not rotating. Now it's just a plug and chug, solve for N2. We get 149 newtons for N2. I don't really care what N2 is. I want to know static friction, which is the same, 149 newtons, because Fs equals N2. I think now with these two problems that we just did, you should be able to do the study guide and you should be able to do those first two worksheets, if not all of them. Okay, the next section I'm going to look at is a little bit more challenging. It's stuff that you need to know for the test in May. And since I'm doing a PowerPoint, I thought I might as well just go all out. Okay, finding the center of mass mathematically. We talked about the center of mass yesterday. It was right in the middle of the meter stick. But if I wanted to find the center of mass of any particular thing, I need to have some kind of relationship, some way of figuring it out. Let's say if I had something that was some weird shape, how could I find the center of mass? Well, it's all related to torque. The net torque of this is not 0, because if I let go of this end down here, it's going to fall. And so it would go around this direction, which is clockwise, it would have a negative torque. But I can use that torque to figure out what the center of mass is. So let's say I want to figure out that torque. Well, what I would do is I would take a little tiny segment down here of mass times g, that would be the weight of it, times its position. That would be the torque that that one creates. I could do that for the next position and the next position. I could add them all up, and that would give me the net torque. So if I add the torque from this, plus the torque from this, plus the torque from that, and add them all up, that would give me the total torque. Can you imagine doing that? This would be pretty complicated. Some people actually yesterday suggested that when I had the meter stick. They said, well, I need to cut off this end over here to figure out how much torque it provides. So you guys were kind of thinking of this already. There's another way, though, to figure out the net torque, and that's just from the center of gravity. And so if I put in the center of mass here, and I take mass of this times gravity times its position, that would also be the net torque. So the net torque is equal to mass of the center of mass times g times the position. I'm going to divide both sides by g and divide both sides by the mass of the whole stick, MCM. Okay, going a little bit further, how do I figure out this MCM? Well, really it's going to be the sum of all those little masses. So kind of like this. And then finally simplifying that or combining it all together in a mathematical form, what it really says is if I take the summation of all of those individual masses times their position divided by the total mass of the whole thing, that will give me the center of mass. Okay, and this next thing we're going to actually apply it to a strange configuration.